The complex logarithm function is defined almost as in the real case. We have argument value set, and we want to find the logarithm corresponding to this argument value, and it turns out to be the solution of this equation. So we want to find the variable w which solves this equation. So given any set, we write this set on polar form. You know that any complex number can be written in this form where r and this theta is real values. So we want now to find this w, and w is also now a complex number. And if we write this complex number in rectangular form, like this, u plus iv, then we can use now the exponential function. We take the exponential function of this variable. We obtain e in this, and we know from the rules of the exponential function that we can divide it into this product, e in u multiplied with e in iv. And well, we know that this should be the value set, and set we already have given this form, so we know that it's r in e and this I theta. So now we already have the complex number on the form that we want. So we know that this must be a real variable, and we have this e in iv, which must be the angle for the total complex number. So what we conclude is that e in u must be equal to this r, and similarly we obtain that e in iv must be equal to this e in I theta. So for the first equation we obtain by taking logarithm that u must be equal to the ln of r, where this is just the real natural logarithm in the real case. And this equation means that this v must be equal to theta plus some integer multiple of 2 pi. So this means that k must be an integer. Okay, since r is the absolute value of the complex number set, we can replace this here. So we have that u is ln of the absolute value of set. Moreover, this angle theta is just maybe taken as the principal argument value of set. So we just write it like this. Recall that when we are dealing with the principal argument value, we use capital A. So when we are adding an integer multiple of 2 pi arbitrarily, we obtain the argument value with small a. So summing up, we obtain that this logarithm, which was the solution of the Bow equation, and we call it w, is equal to this u plus iv, which is now we have now found that this u must be ln of the absolute value of set, plus, and now this v is the argument value of set. So we obtain this expression for the complex logarithm function. So this is now taken as the definition of the complex logarithm function. Remember that in the real case we only have this part, of course. So, and this corresponds to the real case when set is a real variable, at least within some multiple of 2 pi, because in this case the argument value of set is equal to 0 plus 2 pi k, where k is any integer value.